Hello, welcome back. So here we're going to change gears a little, and instead of talking about forces and momentums, we're going to move to a slightly different domain, the domain of work and energy. These are very convenient because they are scalar quantities, unlike force, acceleration, and momentum. So they are more or less easier to work with. We don't have to worry about the cumbersome vectors and those kind of stuff. So to begin, let's look at the first concept, which is kinetic energy. Oh, this is black. I don't like black. I like blue. Blue is better. So kinetic energy. For a particle like this particle mi that is moving in space, we can write the kinetic energy of that particle is 1/2 m its speed squared. So this is a scalar, and we are dealing with the speed. Something we can do is, we know v is r dot, and we can then write v squared. It's the norm of v squared, which you can write as v dot v, or r dot dot r dot. And kinetic energy for a system of particles, so T of the whole system would be summation of all these Ti's that I can write 1/2 summation of mi vi squared, or in that kind of notation, 1/2, this is summation over I, let's do that. Summation over I of mi r dot r, or 1/2 of this, the mi vi squared. Now, one thing to remember, where is my cursor? My cursor disappeared. What happened? These velocities are absolute velocities. So v is absolute velocity. One thing we can do is look at kind of from the perspective of the center of mass. So our reference frame, kinetic energy from center of mass reference point, from COM reference point. So what we can do, we know R of one particle, Ri is Rc plus rho I, and rho I in this case, I cannot do this. This takes a slightly different axis. Okay, this is rho I. And I can use this dot notation to write the total kinetic energy. So T is the summation of mi times Ri dot Ri, which is Rc plus rho I dot Rc plus rho I. Oh, this should be dot. So I'm working with the dotted version of those, the first derivative. So R dot I obviously equals R dot C plus rho dot I. So these are all rho dot R dot R dot R dot, which is going to be some, where is the half? Where is the half? Where is the half? Which equals 1/2. I'm going to distribute these dot products. So I have 1/2 summation mi r dot c dot r dot c is r dot c that norm squared plus 1/2 sum of, well, I will have 2 r dot c dot rho I, so that will cancel with the half. Well, actually, let me write this. 2 mi rho I dot rc plus 1/2 summation of mi rho dot I squared. Rho dot I squared. So in the middle, this one is going to be 0 because I can, this is summation over I can take, these are again R dot, rho dot. I can take out the R dot out of this, and the rest is going to be the velocity of center of mass as measured by center of mass, which is 0. So what I left is T of the whole system, kinetic energy of the whole system is 1/2 m. Let me write it as V of C squared to make it easier for myself. Why is it R2 or C? And let me actually write this instead of that as, oof, what happened? What did I do? Oh, it doesn't work. What was it? I don't remember. It was, it must be MI. Yep. So 1/2, the first time I'm going to write it as total mass times VC squared. And the last one is 1/2 summation mi. Let's keep it as is, rho dot I squared, which is kinetic energy of center of mass, as if we concentrate the entire mass into one point, the center of mass, and the movement of that, plus kinetic energy of internal motion. So this is the first time I think that the internal working of a system becomes important. In the previous videos, whenever we were talking about internal things, we had these internal forces that were equal and opposite each other, and they always cancel out. But here, the kinetic energy, the internal working of a system actually becomes important. So it's not just the motion of center of mass, the relative motion within the system also matters. Okay, that's good. So the other term here is energy. Okay, actually we talked about energy, let's talk about work. Work is also a scalar, as you remember. Work is defined for each individual force. So if I change color, green. So if my object is moving along some path and there are these forces, internal and external forces, acting on this body. So well, actually, let's define first. Work of a force is W. That looks like an omega. Let's write it like this. W is the integral of F dot dr from point A to point B. So this dr is the infinitesimal displacement of the where the force F is acting. And work is also a scalar. So the good thing about the scalars is that we can algebraically add and subtract them without worrying about the direction. So that is the definition of work. In this example, that I have a mass mi subject to some external forces, capital F, and some internal forces, Fij. What I can do is to find the total work that is acting on that particle is integral from A to B of all forces dot dr as my object moves some infinitesimal direction dr, that is what it is, along the path. And I know it is so total force, this is integral A to B of this Fi plus sum of Fij summation over R dot dr. And from Newton's second law, we know this is m r double dot. So what I have is integral A to B of mi ri double dot dr. I'm going to do a little bit of manipulation. Integral A to B mi, instead of r double dot, I'm going to write dr dot over dt dot dr. And I'm going to take this dt mi dr dot now dr over dt. So I'm taking this dt over there. And this is integral of mi v or r dot dv. So this is dv. This is, let me write it. No, it's good. And now my integral has changed from the bounds. I can, because of my variable has changed, I can write it from VA to VB. And this one is finally 1/2 mi v VB squared minus V VA squared. or VB dot VB minus VA dot VA. Okay, and this is, well, kind of, this is called the principle of work and energy, but maybe let me, let's write it as so. So T at B minus T at A, the change in kinetic energy between the 2 points. And I can add these effects over all my particles in my system. So big W, the total work of all forces. So this is total work of all forces in the system, and that includes both external and internal forces, is essentially, I can take the summation, do all of that, so it's going to be TB minus TA. So the final kinetic energy of the whole system minus the kinetic energy at the beginning. And this is what we call the principle of work and energy. And it is what I just said. The total work of all forces acting on a system causes the kinetic energy of the whole system to change. Kind of an alternative way you can write it is take this movement and make it shorter and shorter in a short duration of time. So this is going to be dW equals dt, or divide both sides by dt, w dot equals t dot. That is also another way you can write it. Let me do this. Not good. So when it comes to the bottom of the page, I don't have as much kind of arm support. That's why it is harder down there. So let's see. And one other thing, maybe add here, W dot is called power. So we are talking about the power of all forces, internal and external, equals the rate of change of kinetic energy of the system. Why did I do this? Okay, so that is how we define kinetic energy, work, and their relationship in the principle of work and energy. And with one other short video, we will conclude this section. That would be conservation of energy. All right, until then.